Hi everyone, nice to meet you. My name is Jin-Gu from South Korea. So I'm working for Korea Institute of Science and Technology. We can so shortly call the KIST, from South Korea. Today, I will give a presentation about more target independent Bitcode. This Bitcode is just extended version of the LLVM Bitcode. So today I will explain that. So first I'll explain the motivation of the target independent Bitcode, and then I'll enumerate the target dependent properties on current LLVM Bitcode, and I will to introduce the new compilation strategy. So with the target independent Bitcode, and I will explain the target independent Bitcode in detail, and I will show you application of the target independent Bitcode. So motivation, So some years ago, we wanted to make a virtual machine for the C and C++ language. Like Java, JVM. So at that time, we found the LLVM. So we thought LLVM is the good candidate for virtual machine, for C and C++ language. So at the time, we study and analyze the LLVM, as compared with the Java JVM. So we thought this is the Java compilation flow. So Java compilation flow has the two compilation paths. The left side is the dynamic compilation flow, and right side is the static compilation flow. In the dynamic compilation flow, Java front-end compiler read the Java source code, and then make a Java bytecode, and interpreter or JIT compiler read the Java bytecode and then execute the program on some platform. And right side, in the static compilation flow, Java front-end compiler also reads the Java source code and then make a Java bytecode, and a hand-of-time compiler reads the Java bytecode and then make a binary. So we can execute the program on some platform in this with this binary. So what is the distinctive features as compared with the LLVM? So we thought that Java source code is the target independent. So it means that Java language is not affected by some target machine. And Java bytecode is also target independent. So we thought Java JVM distinctive features as the target independent as compared with the LLVM. And so we thought we imagined the LLVM compilation flow. So left side is the dynamic compilation flow, and right side is the static compilation flow. So in the dynamic compilation flow, LLVM front-end compiler read the C and C++ source code, and in this point, Dragon Egg has the more input language, but we just focus on the C and C++ source code. So front-end generate the LLVM Bitcode, and the interpreter or JIT read the Bitcode and then execute the program on some platform. And right side in the static compilation flow, front-end compiler reads the C and C++ source code and then make a Bitcode, and then ahead-of-time compiler with the code generation path and some path, make assembly code, and then we compile the assembly code to a binary, and then we can execute a program on some platform. And what is the LLVM's distinctive features as compared with the Java? We thought C and C++ source code is a target dependent. This means that C and C++ language is affected by target specific machine. And LLVM Bitcode is also target dependent. So at that time, so we thought LLVM's distinctive features as compared with the Java JVM is the target dependent. So I will enumerate the target dependent property on the current LLVM. So there are three target dependent parts on the LLVM. First is the LLVM front-end compiler and LLVM IR and source language. So I explained the front-end compiler. So sometimes LLVM front-end compiler will generate a target-dependent Bitcode. So for example, it's a function type and the size of keyword and the align of keyword and so on. This is the example, function types example. So when we compile this code, and LLVM front-end compiler generate the target-dependent Bitcode. So this code means just to make the variable on the stack, and then set a variable and then make a call. So this is the generated Bitcode. Maybe a little bit confusing for the beginner. So this is the make a variable on the stack on the x86, and then set a variable like this, and then make a call. So this is so straightforward. But on the ARM, it's also make a stack variable on the stack, and then set a variable, and it's the split the parameters, because ARM ABI is different from x86. So in the ARM, split the variable and then make a call and then pass the argument, each split argument to the callee. So this is the target dependent property on the LLVM. And another example in the size of keyword. So when you compile the left side code, and then front-end compiler make a right side code. So it's different between x86 and ARM, because long double type is different on the x86 and ARM. And the x86 is the long double type size is a 12 byte, and then ARM is the 8 byte. It's different. But LLVM supports the common value, size of value. So maybe I just imagine. Maybe we can use the that size of value and align of value, offset value. So instead of this constant. But maybe there are some problems, because in the C standard, it's the size of keyword is the constant in the compile time. So maybe we modified some standard and then some code in the front-end compiler. Anyway, this is the target-dependent property. And another target-dependent part is the LLVM IR. So in some case, LLVM doesn't support the common IR. For example, it's a long double type and then struct type with the Bitfield. So I'll explain the long double type. Long double type has the various encoding format like this. On ARM, long double type has the 68-bit like this, and x86 has the 8-bit like this, and then PPC has the 128-bit. So long double type has the different encoding format according to the target. So LLVM front-end compiler, so compile this code and then generate this code. So on the x86 and on the x86 LLVM front-end compiler, so generate the x86 underbar FV A type for the long double type, and ARM just change the so double type. It's different. So in this situation, there are some problems because so when we compile the left side code with the LLVM front-end compiler configured with the ARM, and then so we execute this Bitcode on the x86, there are some problems like this. So this code application so pass the parameter double type, and so printf function in the x86 with the x86 FP8 format, 80 type. So when we execute this program, so we have a wrong value and maybe some segment fault. So this is the target dependent property, one of the target dependent property. And so struct type with the Bitfield. So LLVM doesn't support the struct type with the Bitfield. So just LLVM, so merge the Bitfield type like this. Like this, like this. Because long type. So long types align side is different between x86 and ARM. So x86 is a 4-byte and the ARM is the 8-byte. So and so struct types, the whole of struct types align side is the depend on the biggest field is align. So padding byte is different between x86 and ARM. So it is the one of the target dependent property on LLVM IR. And last, source language. So as you know, so inline assembly is the target dependent syntax. So this is the target dependent, and target dependent source code. For example, when you make a code to check the sign bit, so on the long double type. So as I mentioned, long double type has the various different encoding format. So when we check the sign bit to the long double type, so when we make a different code according to the target. So in this case, it's a target we call target dependent source code. So we saw so source language is a problem until now. So maybe we discard. So maybe it's so a little bit, So maybe difficult to implement. So we just discard, and then we focus on the LLVM front-end compiler and the LLVM IR. This is our new compilation strategy. So we just focus on the static compilation flow, not dynamic compilation flow on the LLVM. So in this compilation flow, so front-end compiler reads the C and C++ source code, and then make a target independent Bitcode. So we call this target independent and target dependent Bitcode we call the Wordcode. So because Wordcode is sometimes target independent and sometimes the target dependent. So and next pass is the translator reads the target independent Wordcode. So maybe generate the target dependent Bitcode. and then some optimization path, and then so code generation path. So read this target dependent Bitcode, and then make an assembly code. And then we compile this assembly code, and then make a binary, and then execute the program. So word code, we call that word code. Word code can be target dependent or target independent. So target independent word code has the additional information. So integer type has the align information, additional align information, and then so target independent word code support the struct type with the Bitfield, and then supports the common long double type. And target dependent Bitcode is similar to LLVM Bitcode because has the just the empty additional information. So this word code's advantage is the word code can be useful to the almost passes on the LLVM. This is the word code examples. When we compile the left side code, and then front-end compiler generate the right side code. So all of integer type has the align information from the high-level language. So this representation, so when we decide this representation, so maybe Renato really helped me in this form. So I discussed with my teammate, and then so we decided this form. So integer type has the additional align information, and then so we just make OVM new backend on the LLVM. So OVM is just a clone of the ARM backend, and then so we insert some code and then some modify the code. So left side is the target independent word code. So after translation, target independent Bitcode is changed to a target dependent word code. In this case, ARM. So maybe just change the integer type to a target specific integer type. And so long double types example. So when we compile the long double type, LLVM, our front-end compiler generate the common IR for the long double type, and then translator change this common IR and to a target specific type. So for example, when we compile the left side code, this is just a long addition of the long double type. So target independent word code has the new type and the long underbar double type. And then, target independent word code has the different encoding format, like this. This is the 192-bit encoding format. It is similar to GCC real format. So we make this encoding format, and then after translation, this code changed to a target dependent word code, like this. On the x86, change the x86 on the FP 8-bit, 8 type, like this. And then, result is same. So first line is the original LLVM, compilation flow, configured with the x86. And then second line is our compilation flow. As the result is the same. So on the ARM, it's a long double type is changed to a double type, like this. And then, result is same. And struct type with the Bitfield. So target independent word code support Bitfield. So in the struct type. So like this. And then after translation, and then this Bitcode, this struct type, so change it to a target specific struct type. So for example, when we compile the left side code, and then front-end compiler generate this target independent word code. So this struct type has the Bitfield type. Yeah. So it's possible to insert zero length Bitfield. So also. So when we change the struct type, and then we have to change a related code to access the struct type, like this. So this code just access the C in the struct type. It's a 0 index and the first index and second index. So this Bitcode access the second index. Index x86, so target independent word code struct type is changed to this type. And then related code is changed. It's access index is 3. And so related bit operation like this. And result is same. And so on ARM, it's a struct type. It's like this. And then so related code is like this. And result is same. So this is the application of the target independent word code. So we imagine this model. So like Java JVM. We are front-end compiler read the C and C++ source code, and then make a target independent word code. And this time, we package this Bitcode to some app format, and then some Linux package, and then some browser plugin. And then some device, so change this format to a target specific format on the server, and then on some device, and something like that. So this application's advantage is when the developer make the program, so just compile one time. And so when we make a program with the floating point operation, so some hardware supports the floating point operation, and some hardware doesn't support the floating point operation. But so when we make a program with floating point operation, we have to make software maybe evaluation floating point library version and the hardware support. So maybe floating point version we have to make. But in this model, we just compile the program one time. And then, so this target independent word code can be changed to a target specific Bitcode. So this is the advantage of the using the target independent word code. Yeah, this is my presentation, end of my presentation. So do you have any question about this?